So first of all, you all may know that there's a lot of data available on public cloud platforms. So for instance, providers, they have complete Sentinel-2 archives or similar products available. And on the other hand, also, if we're thinking, or if you're looking into a more into a perspective of methods, we have a lot of methods to analyze these data available. Think of R packages. So in R, there are around 18,000 packages on the official platform CRAN. And of course, many of these methods are interesting to try out and apply on satellite imagery, also on larger scale. But of course, nobody actually wants to download these huge data sets to your local machine from the data portal. So that can be a very frustrating experience sometimes, depending on the particular platform. So the goal for today is really that I would like to show you how you can analyze satellite image collections in the cloud with R. And for that, I'm starting with an introduction about cloud computing in general, about how satellite imagery is stored in the cloud and how you can access the imagery in the cloud. Therefore, I will introduce you to some relatively new technologies, including cloud-native technologies like Stack, cloud-optimized GeoTIFFs, and data cubes. And then I will briefly mention the R ecosystem for analyzing satellite imagery in general, and then afterwards come to a couple of live examples that we will, to get some hands-on experiences, how we can use data cubes and all these technologies from R. So when we talk about the cloud or doing stuff in the cloud, that can actually mean several different things. So first of all, it can just mean that we're using ready-to-use services like Google Earth Engine. So basically, we're just using the browser and use software that runs in the cloud and gives us a nice-to-use interface in the browser. So Google Earth Engine is one example, but of course, there are other platforms like Sentinel Hub, which organizes Sentinel-2 data on Amazon Web Services. And then, other services include some other backends for processing Earth observation imagery, like these OpenEO backends. OpenEO is a European project that tries to standardize how you analyze data in the cloud. And I guess we have a talk by Alexander Jakob on Thursday on OpenEO, also in the Spring School. So that might be very interesting as well. But on the other hand, we can not only use these ready-to-use services in the cloud, but we can also use their infrastructure on a much lower level. So in principle, we can use Amazon Web Services, Google Cloud Platform, or Microsoft Azure to run machines on their infrastructure. So we can just request virtual machines and then pay for them, of course, and then do everything we can also do on our local computer. So these are two different ways how we can do stuff in the cloud, and then there's maybe some platforms that are somewhere in between. And one would be the Microsoft Planetary Computer, which is also very young, and that a bit gives you like low-level access where you can really access virtual machines and also get a terminal and a command line interface and so on. But on the other hand, it has some pre-installed software like Jupyter Notebooks, and also all these libraries that you need for spatial data processing like GDAL and so on. So that's kind of in between, I would say. So in this tutorial today, we are going really on the low-level stuff. So we use Amazon Web Services to run our own machine and then run R inside of that machine to access the satellite imagery that is stored in their infrastructure. So let's look at the cloud infrastructure in general. So this is for Amazon Web Services, but it's very much similar for Google Cloud Platform or even Microsoft Azure. So in principle, the infrastructure is a lot of separate data centers that has large clusters. And these data centers are divided into regions. So for instance, you have regions on all continents, basically. So here it's US West 2, EU Central, and Asia Pacific Southeast. And each of these regions consists of several availability zones. So these are, again, independent kind of data centers to guarantee high availability, so on and so on. So they really are isolated from each other to give you the guarantee that it's not, it's basically highly available, even if for one availability zone is getting no power or so. So in total, for AWS, there are more than 25 regions available and more than 80 availability zones. And the most important thing you know when you want to start with Amazon Web Services and so on is that you want to run virtual machines, and the service you need to use is the EC2 service, the Amazon Elastic Compute Cloud. So then we want to run a machine there, and what we have to do, of course, is first we have to register there and provide some credit card numbers or bank accounts. But afterwards, we can simply select the region and the machine instance type. So, and it's relatively easy. So we can basically, it's in German, too bad, try to find appropriate instances here. So we can just select our desired number of CPUs or so, and then use different general purpose, compute optimized, or whatever instance types, and then see some suggestions and also see how expensive they are. And then basically we can select based on our needs what instance type is appropriate for our analysis. And yeah, we can, whoops, then yeah, go on and yeah, basically follow the instructions on in the browser, and yeah, click launch instance, create a key pair to get access to the machine, and then follow the instructions. And that can all be done from the browser also. So you don't need to connect to the instances via SSH, but it is also possible to access the machines via the browser. And then, of course, you need to install software there. So that includes GDAL mostly, and in our case, our Studio server, a couple of R packages, and some other spatial libraries, whatever you need. Of course, it's a good idea to think about security considerations, but I'll skip that for now here. So then afterwards, if you have started an instance on AWS, you see this browser interface, the AWS Management Console, and there you can really stop your instances as you need them. And then you also pay by use, so it makes sense to stop it if you're not using it. Okay, now that we have a machine running on the cloud, we can access the satellite data. So let's first have a look again at what data are there. So for Amazon Web Services, it's the Sentinel archive, the Landsat archive, but also climate reanalysis data, ERA 5. There's OpenStreetMap data and climate model output, and a lot more, actually. The Google Cloud Platform has also Landsat and Sentinel imagery, and more interestingly, it's possible to access all data that is also available in Google Earth Engine. And then the Microsoft Planetary Computer also has a lot of data, including Sentinel, Landsat, MODIS, and yeah, a lot more. So to be able to access these images on the cloud machine, we need to understand a bit about how the data is stored. Because these instances, so if you run a machine there, you have local storage similar to what you have on your computer at home. So there's a hard disk connected to it, but of course, it's not where the Sentinel data is stored, right? So they use a technology called object storage or S3, simple storage service. And the most important terms for these S3 storage are bucket, object, and key. A bucket is similar, it's just like a container for objects that are stored on a specific region in the cloud. Objects are individual files and corresponding metadata that are located within a bucket and that are identified by a unique key. And the key is simply just similar to a file name or a path to an object. And then what we also need to understand is how pricing works. So always the owner of a bucket on S3 always pays for the storage. And typically the owner also pays for data transfer. So if somebody downloads the data, for example, and for requests. But there are some buckets, so-called requester-pays bucket, where the data transfer and the requests are paid by users. And that's actually pretty often the case for satellite imagery, that you have to pay for the data transfer and the requests. So let's look at some examples. So buckets, for example, are the Sentinel-2 bucket here. We can click on the link and then get these general metadata on the Sentinel-2 data on AWS. So you can find out here that it's a request or paste bucket, so you have to pay for the data transfer and requests. But you also see a lot of tutorials there and use examples, so that's pretty useful, I think, to get started. So another example would be the Lancet archive. So that's a different bucket. And an object would really be the complete URL with one TIFF file. So for example, this is again the Sentinel 2 archive of cloud optimized GeoTIFF files. And then this is the complete URL. You see the bucket name here and the collection name, and then this is really like the URL. If I click on it, actually it downloaded the images just now, or it's just downloading now because it's open to the public. Data access is a bit different. So it's not, the Sentinel data is not a drive on your machine, and basically it works over HTTP. So similar to how browsers connect to servers, right? So there are some challenges involved with that. So the most important question at first is, how can we find images by location, time, and other criteria? So imagine you have your study region and you don't want to scan the full archive of Sentinel data. So you need some kind of service to find only the relevant images that are really inside of your study area. And the second aspect is, and the challenge is, how we can efficiently read these image data from S3 without downloading the complete images to our machine first and then do some kind of processing there. So ideally, we really only want to download the relevant parts of these potentially large files to our machine when we do the analysis. And to solve these challenges, there are quite a few technologies that have been developed during the last 5 to 10 years, maybe. And let's start with STAC. So STAC is a spatial-temporal asset catalog that essentially more or less solves the first challenge, how we can find images by location, time, and other criteria in the cloud. So STAC is basically a standardized JSON-based language for describing catalogs of spatial-temporal data. And that's not only the case for satellite imagery, but also for point clouds or synthetic aperture radar data, or other spatial temporal data, basically. The standard is extensible. It includes extensions for Earth observation data, for data cubes, for point clouds, and a couple of more. And although it's pretty young, there's already a version 1 release available since May 2021. And yeah, the STAC technology is really growing very fast, but also the ecosystem around STAC is pretty useful already. So let's take a look into the specification of STAC. So let's start at the lowest level at the items. So items in the STAC terminology are inseparable objects of data or assets and metadata. So for instance, an item would be a single satellite image. So then at the highest level, we have catalogs that simply group things, right? And then we have collections that extend catalogs and can be used to group items and their metadata again. So for instance, you don't want to put the metadata of license, for instance, in all the STAC items, but you want to group it together to a collection and then provide these kind of metadata at collection level because they apply to all images. So that's kind of the hierarchy of STAC terms, and catalogs can be nested. So maybe let's start with looking at an example. So this is a STAC catalog for the Sentinel-5P data on AWS. So this is actually a so-called static catalog. So that means that it's a JSON file, and this is only the rendered version of this JSON file powered by STAC browser. So this gives us this nice looking interface here, which we can use to navigate and so on. So here you can see that this catalog has actually 4 subcatalogs. So the offline processing stream, the near real-time processing stream, the reprocessing stream, and the cloud optimized GeoTIFF catalog. So let's maybe go to the offline processing stream, and you see that this STAC catalog has again a couple of other catalogs. And in this case, it's the different variables that are measured by the Sentinel-5P satellite. So let's maybe choose methane, and then here you see, separate catalogs for 2020 and 2021. And then you see that you have catalogs for every month and catalogs for every day of month. And then finally, at some point, you see the stack items. And this is really the individual images. And if you click on one item, you basically see the spatial footprint, which always looks a bit weird for the Sentinel-5P data. But yeah, that's just how the data are collected. And then you find some metadata here of this item of the image, in particular the acquisition time. And more important, you see this link really pointing you to the file, to the image file. So if I click on that link, that would give me the netcdf file of Sentinel-5P observations. So and that's nice. So it's nice to browse and nice to navigate with the stack browser technology, but in fact, it's just like the metadata as a set of catalog JSON files. So it's this kind of static stack catalog. So as we've seen, so the catalog JSON contains links to collections, nested catalog, or items. So you have one root catalog JSON file that points you to other files and so on. And that gives the whole metadata description, and in the end, for the items, also the links to the files you are interested in. So the problem with these static stack catalogs is, in order to find out which images are really like relevant for your study area, you must still process all the images, all the stack items once and extract the metadata. And that's not so efficient. And therefore, there is one component from Stack, which is called Stack API. And that defines a web service where you really can dynamically search for stack items by area of interest, by date, time, bounding box, or even other metadata. And that's very useful. And the Stack API is also compliant with the OGC API feature standard. And yeah, we will use that a lot in the practical part. So then as a starting point, I suggest looking at Stack Index. So that's a nice way which indexes available stack catalogs, Stack API endpoints, and so on. So if you're looking for data to play around with, that might be a good starting point. Okay, so Stack basically solved the first question, how we can find the data efficiently on the cloud storage. So the second problem was that we somehow need to efficiently access the data. And that's where the cloud optimized GeoTIFF plays an important role. So the cloud optimized GeoTIFF is simply an image file format that is basically a normal GeoTIFF file where the content is a bit reordered. So so the GeoTIFF files are tiles, so that means they are stored in blocks, so in these rectangular blocks. And then it supports compression, and mostly they also contain these overview images. So they have, or image pyramids, so they not only have the full resolution, but also the resampled lower resolution imagery if you are interested only in doing stuff at lower resolution first, maybe. And the difference to normal GeoTIFF files is that these support these kind of range requests over HTTP, because we are transferring the data from S3 to our cloud instance over HTTP. So if we want to transfer only parts of an image, that's very important, these kind of typical requests. And that's supported if the data follows these rules or the specification of the cloud optimized GeoTIFFs. And the good news is that we have GDAL basically, and GDAL can efficiently read and write cloud optimized GeoTIFFs, and also access object storage in the cloud with so-called virtual file systems. So that's pretty easy to use GDAL and just provide a link to an object or to an image on Amazon Web Services, and that is a cloud optimized GeoTIFF. So it's pretty easy to access it with GDAL, and we don't have to do anything because GDAL solves it all for us. And also because all the relevant tools in R and probably also Python use GDAL to access imagery. That means that nothing has to be done in the R or the Python world to support cloud optimized GeoTIFFs and also access to cloud storage. So that's very good news, I would say. So that's also solve the efficient data access on cloud platforms. The next problem we might face is that the satellite imagery itself is a bit irregular if you process larger areas. So in this example here, you see the footprint of Sentinel-2 images over Western Europe here. And you see that each image actually covers an area of, I think, 100 by 100 kilometers or so. But the images, they spatially overlap, and they come from different UTM zones. And also they have different pixel sizes depending on the spectral band. And if you really stack up these images from different swaths here, you end up with a very irregular time series of images. So for example, if you have like only one tile, then of course you get a regular time series, like every 5 days, one image. But if you then include other tiles, other images, then of course maybe you have an image here 4 days after the image here, and then again 5 days here afterwards, and so on. So that's pretty much irregular in the end. And instead, what we would like to have and to make analysis a little bit easier is often something like that, a multidimensional array or so-called data cube. So in this case, so this is actually just a single data cube here, although you see these 4 cube things here. And this is 4-dimensional. So it has spatial dimensions, latitude, longitude. There's a time dimension, and it has a spectral dimension or a variable dimension with the different channels here. And that's very convenient because all the observations are collected in one object instead of just a collection of images where you have to somehow iterate over the images that come from different projections, and so it's difficult to overlay them and so on. So these data cubes really like collect all observations in one object, and then every combination of dimension values, so the combination of bands, time, and spatial coordinates yields a single number. And also these data cubes typically have only a single coordinate reference systems, and the cells in this case here have constant temporal duration and a spatial size. So they are nice to work with. But we have to keep in mind that the creation of a data cube is basically lossy. So that means if we go from the image collections to the data cube, we first have to think about our data cube parameters. So we need to first think about how our data cube should look like. So what is the appropriate spatial resolution? What is the appropriate spatial reference system? And so on. What is the spatial temporal extent we are interested in? And then we need to apply image warping. So that means reprojecting images, rescaling, resampling, and so on. And that is, of course, that means that we lose information at this step. And then afterwards, we still need to apply a temporal aggregation if we want to yield a regular time series, because imagine that we want a monthly time series and we have a lot of observations within 1 month, then of course we need to apply an aggregation function for images within the month, and therefore also at this stage we might lose information. So what's important here is that there's no single correct data cube for a particular data product, because the spatial resolution and everything depends very much on our needs and on particular analysis. And we have to think about these parameters before. So let's look into the R ecosystem and a couple of packages that are available to process satellite imagery. So first, mostly well known is probably the raster package or the Terra package. So both are general packages for raster data analysis. So the Terra package is rather new, so it's more or less a replacement for the raster packages, raster package, which is in most cases much faster. So the raster and Terra packages support 2 or 3-dimensional rasters, and they include lots of analysis tools, and it's really stable and gives you a very good performance also. So the downside of the packages is really just it supports only 2 or 3-dimensional rasters. And if you have like multispectral, multitemporal imagery, then you need to work around a bit. So, and then you end up with lists of raster stacks or something like that. That can be a bit inconvenient to work with. On the other hand, we have the stars package, which is very flexible because it allows you to define data cubes or spatial temporal arrays with arbitrary number of dimensions. And this package even supports raster and vector data cubes as well. So you can have these regular raster cubes we have just seen, but you can also have vector data cubes where one dimension refers to spatial features, to vector geometries, basically, like polygons or points, or so on. And that's also very nice for time series analysis, I think. Then with the GDA cubes package, and that is specifically aimed at the conversion from satellite image collections to data cubes. So it implements the creation and processing of 4-dimensional data cubes we have just seen from these irregular image collections. And at the same time, it does parallel processing and processing the data only chunk-wise to reduce the memory footprint of the analysis. And also it includes a couple of operations on data cubes that can be applied on the fly. And we'll see this package actually in action a lot in the practical part. Then there's even younger the SITS package, satellite image time series analysis. So this is a very general package full of features for a time series analysis of satellite imagery, and that basically builds on top of the previous packages I've mentioned, and that also includes sophisticated methods, but with a focus on time series classification. So you really also can do the classification steps and the machine learning parts with this package. And it has a pretty comprehensive documentation available as a book online for free, so it's very useful. And you can really do a lot of things with the SIT package. That is also available on CRAN since a couple of months or so, I think. Okay, then there are, of course, a lot of other packages available. Most important, there's RStack. That is the R package to query images from Stack API services. So that's also what we will use in the practical part. Then there's the SP package, which is rather outdated today. So that was is more or less replaced by the SF and stars packages. And for the OpenEO project, if you analyze satellite imagery with OpenEO on OpenEO backend, you can use the OpenEO R package. Therefore, I guess you will learn about the project on Thursday. So here we're going to focus on RStack and GDA cubes mostly. All right, so let's start with the practical part. So I have the examples here on the materials for this tutorial, and that includes the R code and also the output. But anyway, I also prepared for the live demonstration a machine on Amazon Web Services that's already running, and that runs RStudio server. That is pretty much like you work with RStudio on your local computer, but it just runs in the browser. So this is a cloud machine, and what I'm going to show you is basically that I run the code here live. That is written down here. So maybe I can increase the font size a bit. Yes, that should be easier to read for you. Okay, so I prepared 3 different examples here. The first is a getting started example. What we're going to do is we create cloud-free composite images from Sentinel-2 data on Amazon Web Services. So our study area is actually the Córdoba province in Argentina, and we are interested in a cloud-free composite image for, I think, March 2022. And luckily, the study region is given as a geo package file, which I prepared. And so let me just copy that. And so we use the SF package here. We can load the shape, the geo package file with a read SF function. So that gives us an SF object here. And then I'm using the tmap package just to create an interactive map here, which is rather easy. So we just provide the geometry as a shape, tm shape to the tm shape function, and then basically plot polygons on the map. And TMap can automatically do that on the leaflet map here interactively. And that's quite nice to use, I think. So the region is actually small for Argentina, I would say, but it's actually almost half the size of Germany. So it's not so small, I think. So yeah, let's go on. This is our study region, and we, of course, first need to find images that are related to the study region from the CLOUD platform. So what we do is we first compute the bounding box of the polygon. So that's pretty easy. We do that with the STB box function from the SF package. But because we want to run a stack query and ask for images on the cloud storage, we also need the bounding box in latitude longitude coordinate, so in WGS84. So therefore we use the geometry object, the SF object, transform it to WGS84, and then again call the STB box function. So by the way, here this is the pipe operator, so to say, that simply puts the left-hand side argument as a first argument to the right-hand side function. So that means that this becomes the first argument of this function call. And that's quite nice because you basically can write down this workflow, how this data really moves and progresses through the functions. And then this is the right-hand side assignment operator. So basically the result of this function then gets assigned to this variable. So this is our specific syntax, but yeah, I think it's quite readable once you understand what it actually means. Okay, so we've calculated the bounding box in latitude longitude coordinates, and then we can already start using the rstack package to query available images. So let's do that. I'm printing a progress bar here. And then let's see what happens here. So first of all, we load the package with library rstack. We then define our stack endpoint. So this is really like the official URL you can find out on Amazon Web Services where the stack API service runs. And then we use this stack endpoint and apply the stack search function, and then provide the name of the collection, our bounding box, and our datetime. So this is a datetime interval, basically covering March 2022. And then we're posting a request and collect the result items. And that's going to be assigned to the items variable here. So then if we print items, we see that the result contains 385 images. And the result also contains, quite a few metadata about the images. So for example, if we look through the items, we have a features element, and that's basically the list of images. So we can take the fifth image, for example, and then print some properties, and then get some metadata for the fifth image in the list. So for instance, we see that this image, had basically no clouds. We can see the projection, we can see a lot of other metadata, and very important, of course, the time of acquisition. Another important field of the stack response is the assets object, and that basically contains the links to all the images. So we see here all the spectral bands from the Sentinel satellite. And for example, if we are interested in the near-infrared image, we can see the relevant metadata here, including the reference to the actual file on Amazon Web Services. And then also some more metadata like the name of the band, the common name, near-infrared, and the central wavelength even, and other important things. Okay, let's go on. So that's a lot of metadata. So what we want to do is in the end to compute a cloud-free composite image, and therefore we're creating a data cube, and we're using the GDAL-Cubes package for that. And the next step is to create a GDAL-Cubes image collection object. So as I said, image collections are basically what comes from stack, and then we need to create a regular data cube from that. So let's just run it. Okay, what we see here in the code is we use the stack image collection function, and that can convert the response or the result from the stack query to a GDAL-Cubes image collection object. So this image collection object is simply just like an index that knows where images are located, when they have been recorded, and where they are stored, and so on. So they're not storing actual image data, but really only links to the data. So very similar actually to the stack response. So we provide here the result from the stack response as a first argument, and then we are explicitly listing all the names of assets we are interested. So to say the spectral bands in this case. So we are doing this here because by default, it only includes spectral bands with a certain kind of stack metadata. And in this case, we are very much interested in the SCL bands. This is a scene classification layer that includes per pixel cloud information. And because we want to include this in our image collection, we explicitly list it here, although the stack reply didn't contain these specific metadata for that band. So we need to work around that a bit and provide these names explicitly here. And then at the same time, we're applying a function on all stack items, on all images, on the properties of the images. And so basically what we're doing here is we are only interested in images that have a cloud cover less than 20%. So we're throwing away all other images and only include these images in our GDAL-Cubes image collection object. So when we print that object, we get basically a list of images and spectral bands that refer to the collection. So we still have like 227 images and 12 bands. And this is a few of them. And we have, the spectral bands as requested. Okay, so that's an image collection object. The next step is really think about how our data cube should look like. So in what spatial resolution we are interested in, and what spatial temporal extent, and so on. And to define that, there is a so-called cube view function. So this is what the GDAL-Cubes package refers to as the data cube view. So it's just a geometry of the cube. So here we say that our data cube should use a web Mercator or spatial reference system with pixel size 500 by 500 meters. The data cube should have 1 day temporal resolution. We're using a temporal aggregation method median. So that's basically the method that is applied when there are 2 images at the same time. It's the same day in this case. Right. So if we would, for instance, say here we use a temporal interval of 1 month. So as a temporal resolution for the data cube, that would mean like we are computing the median values within the month. So for 1 day, this is probably doesn't matter so much because we have a 5-day revisit time for the Sentinel-2 satellites. And then we're using a spatial sampling algorithm average because we are pretty much reducing our spatial resolution. And then we define our extent, so the start and end date and time of the data cube and the bounding box, basically. And that's how our data cube should look like in the end. So we can print that object and see the dimensionality and everything we've just set up. And afterwards, we can almost create a data cube. So what we do is, we still define a mask. So because we have the scene classification layer band here for the Sentinel-2 images, and that is basically a categorical variable that encodes some yeah, some properties like 3 stands for cloud shadow, 8 and 9 is cloud medium and high probability. And that's what we want to know. And if a pixel has one of these values, then it will not contribute to the data cube. So we set it to an A before the data cube is created. So that's basically what this mask does. And then we can really like create a data cube. And this is what the raster cube function does. So we put, it takes the image collection as input, the data cube view, and optionally the mask. And then it gives us a data cube with, well.
Marius?
Yeah.
May I ask you a question?
Sure.
When you apply this mask, being this a data cube of 1 month of data, how does this image mask work? Like, does it aggregate all the SCL bands for the different dates?
No, the mask is actually applied per image, really. So
okay, per image.
Before they're combined.
Okay, perfect. Perfect. Yeah. Good. Thank you.
Sure. All right. So then really like we're just combining the things in the raster cube function, and then it gives us a data cube. So one important thing with GDAL cubes is that it's not really loading images now and not doing expensive computations. Instead, it just gives us a so-called proxy object or a virtual data cube, so to speak, that just knows what to do when we call plot in the end. So when we really are interested in the results or do something with the results. So that's, yeah, one thing we have to be aware of a bit, that although we created a data cube just now and have the object here, it just hasn't read any data, image data yet. So it's just derived the shape of the output and so on. And yeah, that's pretty much everything it does. Okay, but now it gets more interesting and really let's do things. So we take the input data cube, apply a function on it. Maybe let's just not call plot for now. Then apply a reduce time function. So that basically takes the time series of daily data cube values and apply on each band the median operation again. So that is just, we have a data cube with 30 values or 31 values in time, and then we're basically collapsing the time into a single value, which is the median value per band. So that is just what the reduce time function here does. And then afterwards, we just crop the image with the polygon. So let's do this. And as you see again, it's again not loading any image data. So if I call functions on that data cube, it's still giving me only a virtual data cube that knows what to do, but it doesn't do it because I haven't called plot or export as netcdf or write a geotiff or something like that. So that's also sometimes called to or referred to as lazy evaluation. That sometimes can be pretty good to optimize things later on. So for instance, if I'm now only interested in a very small region in the end, then I can really optimize the beginning of this chain of operations because I don't need to load all the images in the first place. So that's sometimes possible if I do it like this. So, but now let's really run the computations. And of course, now it takes a bit longer. So you get a progress bar. And then things are really read from Amazon Web Services. The image data is read, the data cube is constructed, and all the operations are performed. And then in the end, you hopefully see an image once it finishes. Yeah, exactly. So, and I think that's almost cloud-free, I would say. So that's a very simple way to get a cloud-free composite image simply by just deriving the median value of time series. But yeah, it's already pretty effective. I have a second example how to do it more complicated. And yeah, maybe let's go to that example directly here. So in this example, we're doing very similar operation, but now we're using the reduced time function not to apply one of the built-in operations. So we've just used the median function, and that is just built into GDAL cubes. But we can also apply a user-defined R function on each time series independently. And that's basically what we do here. So we additionally need the near-infrared band, because in the function we basically calculate the NDVI vegetation index, and then we are selecting the day of the month which has the highest NDVI value, and return the RGB bands at that particular day. So what we provide here is a function that calculates the NDVI. So this function gets basically one time series as input and can access the spectral bands as a first index and the day as a second index. And then we have one NDVI vector here. We have to do some error checking here because, of course, because we crop the polygon, we have a lot of time series that are full of NA. Then we have just to make sure that this is not just stopping our computations. So if the full time series is basically NA, we also return a vector of NA values. And then we just calculating the day at which the NDVI has the highest value, and then returning the RGB bands. And then, let's try that out. That might take a few seconds more, I don't know. It should give us an image that looks very similar to this one, but probably a little bit greener. So let's wait a few seconds. Yeah, done. So I don't know if you could see it, but at least here it looks now a bit greener. So yeah, that's kind of a getting started example with GDAL cubes and doing everything in the cloud with Stack and cloud optimized GeoTIFF, Sentinel-2 data, and so on. Of course, there are a lot of other things we can do, and we will see some of them in the next examples. But also what I skipped here in the meantime is that the GDAL cubes package has a lot of other functions built in. So you can do spatial or temporal aggregation as well. You can apply functions on a per pixel level, like to compute vegetation indexes and so on. You can fill time series with simple time series interpolation methods. You can filter pixels by arithmetic expressions. You can also combine two or more data cubes that have identical shapes, so that can sometimes be useful if you want to really build combined data cubes with, for example, Sentinel-2 and Lancet data. And then there are a couple of other options, methods that are useful. And if you're interested in that, please feel free to try out things. All right, so let's go on with the second example. So this is
Marius, before we go on with the second one, there was there was a question from Priscilla here, but okay. She wrote that you just answered the question. Okay.
All right. Yeah. No, feel free to interrupt me at any time. I just don't see the chat also, so I might not realize.
Yeah, I'm taking a look at it, so no worries.
Oh, okay. Thank you.
¿Hay alguna pregunta por ahora sobre todo esto? Por si quieren. ¿Qué? Okay. They are absorbing information, they say.
All right, good.
Okay, just go on.
Okay, so the second example is actually very similar. So we're doing time series analysis, but with different data sets. So we're using now MODIS vegetation index data on AWS and apply some more complex time series analysis, in this case, trend estimation and change detection. So the most important difference to the previous example is really that this data is served on a requester paste bucket on AWS. So that means we cannot access it directly as the Sentinel-2 data. Instead, we need to specify a few options. So what we need to do first when we work on AWS, we need to create a user with S3 reader rights. So that's something we have to set up before. And then we get these key ID and access key ID, and we need to fill that up. So I have done that already in the session. So I'm able basically to access the imagery on this machine here. But otherwise, the workflow is exactly the same. So we define our area of interest. I can do that now, which is the country of Germany now. So I can also plot it. That is, we're only interested in the overall geometry, so that's not too important what's in the data here. So what we then do is really, again, derive the bounding box, convert the feature, the geometries to WGS84, and then afterwards call stack. We use a different endpoint, of course, because it's a modus data, and we use different collection name. But other than that, it's pretty much the same, but with different data sets. So let's request some images from stack. So that's taking a bit longer here because it's probably more data, because our time of interest is basically 10 years now, from 2010 to the end of 2019. So the result should contain something like 707 images. And then the next step again is to create a GDAL-Cubes image collection object from that stack result. So let's try that. And we end up with all the images in an image collection object. And then next, we again think about our data cube geometry. So in this case, we are interested in the full 10 years, but that's maybe a bit more interesting here now. So we're using this cube view function again and provide the spatial and temporal extent. So we're interested in the 10 years and do this on 1 kilometer spatial resolution. I think the original imagery is 500 meters, but for now, for the example here, I think 1 kilometer is acceptable. And then we're actually using a temporal duration in the data cube, or a temporal resolution of 1 year, and an aggregation method of median. So that means I have 10 years of data, and the images of 1 year will be reduced to with the median function. And then the data cube has only 10 values in the time dimension, so 10 years. And so that's basically what this aggregation and time interval here does, right? So that means, but I'm using all the data anyway. So I'm not using only one image of a year, but all images of the year when we create the data cube. So in this case, we're doing a simple trend estimation here, and we again using a user-defined R function here. So we're using the quantile regression R package, and then doing basically a quantile regression with calculate the NDVI, create a time variable that just has a year after 2010, and then explain NDVI by time to get simple trend coefficient, right? And that's more or less robust because we're using quantile regression here. And then we can run it. It might take a few seconds, I would say, or maybe a minute. So what we're also doing here is that we're selecting the bands first, so only the NDVI band. And afterwards, we're cropping the result again with the shape of Germany here. And then we write the result as a net CDF file. So we're not plotting directly, but really export the result as a net CDF file. So let's see if it starts doing things at some point. I should have started this earlier. But let's see. Okay, it's doing things at least. So yeah, maybe I can go on here with the explanation while it's computing. Afterwards, so the result is a netcdf file, and that has only one single band and only a single time point. So that means we can really use, for example, the Terra package directly, or we could also use a stars package to load this file. So we can then use the Rust package from the Terra package, load this netcdf file, and then again use the tmap to create an interactive map. And then we end up with this map of Germany, which doesn't look too interesting. So surprisingly, it tends to green up in some areas, but if you zoom in a little bit, you see that there are some interesting areas basically where the NDVI goes down quite drastically. And that's due to some surface mining activities during the last 10 years there, which have been increasing a lot. And of course, some deforestation at the same time. Okay, so that's a very simple example for the trend analysis. And we can also do, very similarly, apply some change detection algorithm. For instance, let's just create a different data cube view. So that means a different data cube. So with a reduced temporal extent of the data. So here we're creating a monthly data cube, but only for 2 of the 10 years. So 2017 and 2018. And we're using monthly temporal resolution, and then basically create a new data cube. And then we similarly really apply a change detection method here. So we again using the NDVI observations. In this case, we're using the BFAST method, which is a very comprehensive method for change detection. And we then basically build a TS object. So that's needed to time series object that's needed as input for the BFAST monitor function. And then we're using the BFAST monitor function to find changes in 2018, given that 2017 was a kind of a stable history where there were no changes, which is, of course, assumption that might not be realistic here, but just as an example, that's how you could do something. And compared to the previous example, what we do here is we return 2 different bands in the output data cubes. So that means that the result has only a single point in time, but 2 different bands. And again, we're writing this as an netcdf file. So I think that takes a bit longer because the BFAST method is really computationally pretty expensive. I can try to run it here, but I don't know. Maybe I have to cancel at some point if it's taking too long. But anyway, we could look at the results here. So in this case, I'm using the stars package to read the result, and the STS stars function that can convert these data cube. So that's NCDF cube is a function from the GDAL cubes package that just loads the result of your previously created data cube. And then it's converting it to the stars object. So stars is a different package. So that means also we can apply any kind of other analysis using the stars package afterwards. And then we are assigning it to the changes stars variable. And then we are just extracting the first and the second bands. So they're called attributes in the stars world for now. And then again, we are using the tmap package to create 2 different maps. And that's what you can see here, I think, and then you find some areas where there have some there were some pretty strong storms going on, where you see some distraction in the forest and in the mountains, so to say, parts of Germany. All right, so it's done here. So I guess, I don't have to repeat this now, because I think the third example might be even more interesting because it's so similar to the previous example. Okay, so let's go on with the third example. In many cases, we're not interested in the full data cube, but we're interested in extracting only values from a data cube at irregular locations. So, and that's pretty much important for machine learning models where we want to extract some training data. So for instance, we have labeled data, something like ground-based collected land use or land cover data, or we do want to do some spatial or spatial temporal prediction or some change detection. And in these tasks, we often need a lot of or a large number of training observations to train machine learning models. And also we can use GDAL cubes to extract some data from labeled points. So in this case, we are using point data of land cover from the so-called European Land Use and Coverage Area Frame Survey. So that's like a program in Europe where they define locations of samples where they really collect land cover, land use, and also soil properties on the ground. And it's a data set you can download for free. And it's available as CSV files. And in this case, we use the point samples over Germany. And in this case, to reduce the computation times for the tutorial here, for the live part, we only use observations of the common wheat land cover type. So, of course, it might be interesting to look at different crop types and different land cover types as well. But for now, let's just use this type. Okay, so in the first code example here, we read the CSV file. So that's really the original file from the Lucas survey with the point samples. And the first step is that we need to convert the CSV table to a spatial object, to an SF object. So at first, it has some columns, th lat and th long, which is the coordinates of the samples. And at first, we had to do some cleaning, so because there were some coordinate values missing. So we had to remove these rows from the table. And then afterwards, we could convert it to a spatial object with STSF and provide the names of the coordinate columns and the coordinate reference system. And then we're just parsing the date and time information using the sdate function and the appropriate column, survey date. And then I'm printing here a few samples. So we see that this LC1 column represents like the dominant land cover type, and this is encoded as these letters with numbers. And the feature we are interested in, the common wheat, is actually B11. So in total, it's quite a few observations. So it's more than 25,000 observations. So it's a pretty cool and useful data set for doing land cover analysis and classification, I would say. So let's go on. For the example, what I do now is I simply find samples with B11, so common wheat samples. I'm only interested in the time and in the land cover columns and in the coordinates, of course. And then I'm using the dplyr package and just create a sample of 100 observations of common wheat. And I store the result in the training sites variable. So let's do that. And that's the sample for now. So there's 100 common wheat observations from the Lucas data sets, and that's of course as expected because we do random sampling. It's scattered all around Germany basically. So that means that if we load or if we want to really like find the values of say NDVI or so, or other properties, we need to load quite a few Sentinel-2 images. So that's quite some work to get the values for all the samples. So what we do first, again, is we query images from our stack. That might take quite some time now, because what we do here is a bounding box query, and it's a bounding box of the complete part of Germany, and the time when the samples have been collected was between April 2018 and September 2018. So there are quite a few Sentinel-2 images collected over that time period over all of Germany. So it's quite a few images we see here. So the result we get here can look a bit different to what is here in the HTML output on the website because it's just a different samples. So we did random sampling, so it's just different now in the live part than in the part you see on the left. So let's see how many images relate to the sample bounding box, so to say. Okay, so it's more than 5,000 Sentinel-2 images. Of course, we're not loading all of them. So what we do is we create a GDACubes image collection again. So one thing I found out here is that the Stack API had some duplicate entries, so I needed to remove it. I don't know really why, but it's something I need to investigate a bit more into detail. So anyway, we have a GDACubes image collection now with the Stack image collection function. And so again, we're just interested in cloud cover less than 10% here, and that gives us still almost 2,000 Sentinel-2 images, which is still quite a lot. So next, we create a data cube. So I guess we can skip that. So that's just that I stored the image collection as a file and then I'm reloading it, but I skipped that because we already created it. And then, yeah, I create a data cube view and the data cube. Let's do it all. And then I end up with a pretty large data cube. So I use really like the original resolution, 10 meter, and the original time interval, 5 days. For the analysis, because I really want to extract the actual values that have been collected and recorded in the images. So that's a very large data cube, right? So that would take enormous amount of time to load and also to process, and a lot of storage on your disk if you really want to download it. So that would be very inefficient to do. So instead, what we luckily can do is find only the images that are really like relevant for our point, and to extract points now from this data cube, which contains the NDVI observation here. So I've used this apply pixel function here to compute the NDVI. So I'm skipping the other bands, but of course they could be integrated as well. So what I do now is using the extract geometry function. I'm running it now, but it also will take some time, I would say. Provide the data cube as input, the training sites as an SF object, and then simply tell what the temporal column is. And then it's basically just overlaying the point samples with the spatial temporal points with the data cube, and then extracting the values. And it's clever enough that it realizes it's not an option to load all of the images and read all the pixels, but it realizes that most of the parts of the data cube are not interesting, so it will be skipped. So now it's done basically already. So let's find out what's the result. So the result has 41 observations because there were quite a few observations where there were only an image with cloud or so. So the result doesn't contain any NA measurements of the NDVI value. Simply maybe there was no image available, or there were just clouds. So we end up only with 41 observations, NDVI, and then of course we can, the result is a data frame which has a time column and NDVI value from the data cube, and this column feature ID, which is the row number of the original SF object. So that can be used to combine the data frame that comes out with the original spatial data set. That's what we do as the next step. So we're using this merge function here, and then use the data frame result we got from the extract time function and join them basically by the FID column, so that we combine them simply, and then we can plot the samples with NDVI values. And then in the end, we actually end up with a table, and then that could yield some training data for some machine learning analysis afterwards. Of course, then it would be more interesting also to include other variables, other vegetation indexes, and so on. But for now, I think that's pretty much it. So before going back and starting with the quick discussion and summary, I just want to tell speak a few more words about this extract geometry function, because it can do different things. So in this example, it was a point data set, right? So in this case, really, like every point yields one value in the result. But it can also be like polygon data, where you, for instance, collect a forest or so as a polygon, and then it includes all measurements within the polygon. So you have multiple rows for a single feature with the same feature identifier. And similar, that also works with line strings or other geometry types. So it's really like a general function where you can overlay data cubes with spatial temporal geometries. And then, of course, you can skip the time column attribute. So if you're just using spatial points or spatial polygons, you can use that, skip that, and extract a complete time series of the observations. So then end up with a complete time series from the data cube at these specific locations. And that's what I did here in the tutorial. Also, it's very much the same. I'm just skipping the time column argument here, and then I get the complete time series, and then I'm just using the ggplot2 package here to plot these time series of individual features, and then I end up with something like that. So this is not a very nice plot, but it gives you an idea that you end up with a kind of a typical time series for common wheat in Germany or something like that. And then, of course, it would be interesting to use for time series classification of crop types or something similar. All right, so let's go back to the slides and just summarize, wrap up, and see a few limitations of that approach. So I think the workflow I've presented and we've seen is has a couple of advantages. One is that we can really directly access Sentinel data on the cloud. We don't need to download anything, and so it's pretty nice. And it's also very flexible because you can do whatever you want because you have a cloud machine. You can install software as you want. You can use R packages as you want, even custom ones, and really try out things as you want. And there are also quite powerful machines available on AWS, even with powerful GPUs if you do deep learning or something like that. So that's really flexible and can be very powerful. And also one good argument to do it like this is also that it's really relying only on open source software. But of course, there are a couple of disadvantages. One is important that it's not free, so I have to pay for the cloud instance and for the data access. So this is certainly something to have in mind. And of course, Google Earth Engine or other approaches that can be easier to use, and some are even free, like Google Earth Engine for research purposes. However, you can't do everything in Google Earth Engine, right? So if you really want to try out methods from an R package, then you need to do something else. Right, so also a disadvantage might be that depending on your institution, you already have like a powerful computing center that have more resources, and that's basically for free. So for instance, here we have a pretty large cluster with powerful GPUs, and if we do really like large scale deep learning, we can use it and don't need to pay, and that would be very expensive on cloud platforms. Yeah, of course, it requires some setup and some familiarization needed, and yeah, it also depends a lot on the existence of Stake API services and imagery as cloud-optimized geotiffs. And that's something currently that there are not so many Stake API endpoints available for free, but I'm pretty optimistic that it might change in the next years, because I think this is really the right open source cloud native approach to do satellite image analysis in the cloud. But of course, it brings me to a different question, or the general question, which tools, platforms, and environments to choose to do analysis. And I think the answer is not so easy, and that's what approach is most efficient to you really depends on your particular needs, and also on the data volume, the computational effort, the data and method availability, but also the effort needed to re-implement things. So, as I said, the example, if you want to apply a custom R function that is available as an R package on your data, it might be useful to do it well as in this presentation, but instead if you're very much familiar with Google Earth Engine, it could also be efficient if you re-implement the analysis, but that pretty much depends on how complex that is and how much effort this is. So let's wrap up and then leave some time for questions. So I think we've seen that these cloud computing platforms contain lots of satellite data, but also that we need to understand a bit how the storage works, because it's a bit different to how we work locally. And then we have seen quite some technology and tools that help with working on the cloud. It's Stack, and especially Stack API, that we can use for efficient and standardized search of spatial temporal satellite imagery. We can use cloud-optimized geotiffs that allow really reading only parts of imagery and also on lower resolution fast. So in these examples, on the cloud-free mosaic images, this is really just only possible because we have cloud-optimized geotiffs that allow to get lower resolution imagery first, right? So we don't need to read the 10-meter Sentinel data first, but we can really just do it fast. And then we've seen that the GDAL cubes package can make the creation and processing of data cubes relatively easier, at least in R. And then, most important probably is that all the open source software that does similar things relies on GDAL, and it's really awesome to have GDAL because it has everything for efficiently accessing data on cloud storage and efficiently reprojecting imagery and supporting different file formats and everything. So that's really like the most important part of the whole workflow, I would say.